Okay, so this is the second part of the problem on the motorcyclist that we have cut off from the previous video lecture. Okay, so we are now actually on the part B where the where is the motorcyclist when his velocity is 25 meter per second. Okay, so the solution for this one is that instead of 23 meter per second, take note that in the previous um, question, we have solved already for the final velocity, 23 meter per second. So, in if we're going to assign 23 meter per second here, what is actually being asked in letter B is a later is the position at a later velocity. So that means when the motorcycle moves at this position, his velocity is 23 meter per second, continuing the motion of the object so that the motorcyclist will now have 25 meter per second as its velocity. So the question is, where is the motorcyclist located with respect to our measuring position of the location of the signpost? Okay, so in the set of givens, instead of having the final velocity of 23 meter per second, we replace it with 25 meter per second. Now, what is being asked is, of course, the position. Now, going back uh, to our set of equations and our described technique, what again the prescribed technique here is for you to make inventory list of all the givens and unknowns, and you compare that with your available set of equations, and you choose from the set of equations from your inventory list that would comply with the number of elements in your equation. So for example, you should realize that eventually we will be led to make use of the second form of the equation, since we are or the fourth form of the equation for answering the question of letter B, since that we are asked to get the final position x, we are given x sub o, we are given v as 25 meter per second square, and we are given in the initial velocity v sub o as 15 meter per second square, and we are given the acceleration a 4 meter per second square, 4 meter per second square. Now from those set of equations, you should realize that this is the most available, most appropriate equation, since we are not given the time of travel between having a speed of 23 up to a velocity of 25. So we're not given the time interval in between. So therefore, we make use of the equation that does not have the quantity time in its form. Okay, so having said that, we now make use of the fourth equation in order to solve for the final position x. So from the form of the equation, we solve for x. Transposing negative x sub o to the other side, you have x sub o. Okay, so making the necessary substitution, you have x sub o as 5 meters plus v square, you have 25 meter per second square, minus v sub o is 15 meter per second square, divided by 2 times the acceleration 4 meter per second square. So 25 square is, of course, 625, and 15 meter per second square gives you 225. So that is 625 minus 225, that gives you 400. 400 divided by 8 meter per second gives you 50, then plus 5 meters, that gives you 55 meters. So 55 meters therefore is the distance traveled by the car from the starting position up to ending up to a position with a speed of 25 meter per second. Okay, so let's continue our discussion on motion diagrams. Okay, so since we already discussed the several motions regarding the motion along a straight line with displacements, velocities, and acceleration, it is now time for us to make the interpretations of the motion diagrams that were presented from the previous video lectures. Okay, so let's consider the simplest of the motion diagrams. We have no motion or an object is at rest. Okay, so a body is at rest when its distance relative to other objects in the surrounding is not changing. Now, so for example, our fixed position is the position of the tree. If we're going to consider this as our origin, a person that is at rest with respect to the location of the tree is the person that is having no change in position with respect to the location of the tree. So when we say that there is no change in position, then we say that the object is at rest or the body is not moving. So for example, this person here is at 10 meters to the left of the tree. The person is not moving since its position is not changing with respect to its position with respect to the tree. The same goes with this other person. Okay, so no motion or an object is at rest for displacement, velocity versus time graph represents the following diagrams. So, for example, this is the location of the tree. Then the object is at that location, the person is at that location, and of course, time always moves forward. This means that the red line represents the position of the person all the time, because time progresses forward. So, although time progresses forward, the person does not progress in terms of its displacement. So, the line would simply represent a straight line horizontal at the starting with the origin, progressing towards the right for the given time. Now, if the object is at a certain location, for example, the person is at this location, the person is 10 meters towards the is 10 meters at the right side of the tree. So in our motion diagram that is represented by this graph, so the person is at 10 meters all the time as time progresses. So that means the motion diagram would be represented accordingly as a straight line horizontal drawn from the location of the 10-meter distance moving towards the right direction. And lastly, when the person is at the left side of the tree, the person is not moving with respect to the tree, the person is at 10 meters from the left of the tree, then the corresponding motion diagram for that would be this one. The person is at a distance negative to the left of the tree as time progresses. So that is equally represented by a straight line horizontal drawn left to right. Okay, so this is for the position versus time graph or displacement versus time graph. The graph on the right is the velocity versus time graph. Now, to represent no motion or the object is at rest for a velocity time graph, try to notice that they have somewhat similar or similar forms of the graph. They are both horizontal straight lines. As time progresses, the object is at a certain location. So the only difference between these two is that you do not specify the position, but you specify the value of the velocity. Now, an object is at rest has a velocity of 0, so therefore your straight line horizontal line is would simply drawn from the origin, progressing towards the right. So this is the representation of an object with no motion or an object at rest for both the displacement versus time graph and the velocity versus time graph. Okay, so the displacement time graph is a horizontal line. When this line is above the timeline, the object is located on the positive x-axis or y. Then the line is below the timeline, the object is located on the negative x or negative y. The velocity time graph shows a line which is at the timeline for velocity equals 0. Okay, so let's consider another set. Interpretation for displacement and velocity versus time graph for uniform motion. A body is moving uniformly at a constant velocity when the distance it moves are equal for equal time intervals. Okay, remember uniform motion. This is the motion of an object with covering equal distances at equal time intervals. So for example, in our example for the tree, instead of having a person, we have a car. Okay, so a car that is moving with uniform motion means it is covering equal distances at equal time. So for as illustrated here, the car is at 5 meters to the right of the tree at time 1 second. If the car moves uniformly, then it covers 5 meters for every 1 second interval, so that it would maintain the speed of 5 meter per second. If it is going to the right, the object is said to be to have a positive direction for the velocity. If it is moving towards the left, then it has negative velocity. Okay, so the corresponding representation of the displacement versus time graph and the velocity versus time graph for uniform motion. Okay, so what we see here is that you have a diagonal line sloping upward. Remember, in a displacement versus time graph, the slope of the line represents the average velocity, as discussed in the previous video lectures. Okay, so on the other hand, if the line is actually sloping downwards, then this means that you have a negative velocity, and a negative velocity is interpreted as moving towards the opposite end, or the left direction, or the downward direction. Okay, so uniform motion is, of course, is motion with constant velocity, and since the velocity for a displacement versus time graph is represented by the slope of the line, therefore the slope of the line here represents the velocity, and velocity is constant, therefore the slope is constant. So correspondingly, in terms of geometry, the geometry for a constant velocity is that you have a diagonal line either sloping upward for positive sense of the direction of the velocity, sloping downward for the negative sense of the direction of the velocity. Now, for the velocity versus time graph, instead of having diagonal line, we have horizontal lines, but it's either above the timeline or below the timeline. Above the timeline representing positive sense of the direction of the velocity, below the timeline if the velocity has negative sense of direction. Okay, so take note, this is east and north, this is supposed to be south and west. The displacement time graph is a diagonal line when the line is above the timeline and the body is moving towards the positive x or positive y. When it is located below the body, below the body is moving towards the negative x or negative y. On the other hand, velocity versus time graph shows a horizontal line either above or below the timeline. Okay, so last of the types of the motion, we have motion with acceleration or accelerated motion. Of course, a body is accelerating when the distances it moves are increasing or decreasing during equal time intervals. So for example, we have here, you have an increasing distance covered by the car for every time interval. So 5 meters, 10 meters, 15 meters correspondingly for each time interval. And the only difference on the right side and the left side is that the car is moving towards the right and the car is moving towards the left in our diagram. Okay, for the displacement versus time and the velocity versus time, we have the corresponding interpretations and forms of the line. For displacement versus time graph, accelerated motion is represented by curved line sloping upward or going upward for the positive sense of the direction. On the other hand, if the graph is curving downwards, then that means that the direction of the object is either towards the negative sense of the direction towards the west or downwards. Now, of course, the line is curved, representing different value of slopes if we're going to choose any 2 points. For example, the slope here would be different from the slope here near the base. That means that they have different values of velocities. Of course, if you're going to have an object covering different distances at at equal time intervals, what that means is that you will have different values for the velocities because you will have different slopes for any combination of points. So that means you have a curved line going upward for the positive sense and a curved line going downward. Now, for the velocity versus time graph, the representation of uniformly accelerated motion is a straight line diagonal sloping upward for the positive sense of the acceleration, sloping downward for the negative sense of the acceleration. Okay, so the displacement time graph is a parabola which opens on the displacement line. When the line is above the timeline, the body is moving towards the positive x or positive y. When it is located below, the body is moving towards negative x or negative y. On the other hand, velocity versus time graph shows a diagonal line above or below the timeline. Now, deceleration is slowing down of an object. The corresponding changes in the forms of the graph are the following. It is the same as before, but this time it is a parabola, but is opening with respect to the timeline instead of the displacement line. Now, for negative acceleration, simply if the object is moving towards the right direction but is slowing down, the corresponding interpretation is that you have a graph sloping downward. And if it is moving towards the left but is decelerating, the object is will have this corresponding form of the graph for velocity versus time graph. A displacement time graph is a parabola which opens on the timeline. When the parabola is above the timeline, the body is moving towards the positive x or positive y. When it is located below the body is moving towards the negative x or negative y. On the other hand, velocity versus time graph shows a diagonal line above or below the timeline. Okay, so this ends our discussion on kinematics.